All right, before we get rolling, please remember that today I've got important exam. So if you're in spot, just let me know. We'll get together later. I don't have any homework for you yet. I'm still figuring all that out. Let's try to adjust the rest of it. But the next one we're going to talk about new stuff, and I'll talk about new stuff later today. Math club today. Freeman, who's a very good speaker, is going to give us kind of a heuristic approach to criminals. That sounds like a lot of fun to me. Theorem. Let the field distinction. Okay. Contains polymer equivalent. Number one, F is cyclic order. So first, among our equivalent conditions is F is a cyclic extension, Galois group, ZD, where D divides N. F is a splitting field. Some polynomial. N minus N, KX. X splitting field of polynomial. You can actually reduce that down to the D, since D is a divisor of this. So I'm going to specialize further beyond this theorem to what we call cyclotomic extensions. Let me tell you what this is in the first place. Latavia field had a cyclotomic extension of order N, and this is I'm following convention on this. I'm not a super fan of calling it order N this way, and I'll explain why I'm not a fan of it. So, for example, their terminology work over here. Over Q, we have X minus 1 right. So if you join a first root unity, to Q. You're just sticking 1 on Q, you get nothing. No big shocker there, right? Well, by their definition, an order 2, you would join a root base squared minus 1 plus minus 1 minus 1. Again, you get nothing new, right? Because plus 1 and minus 1 are in there. Order 3. This is actually a quadratic extension, right? So actually, let me kind of write in parentheses over here. Actually, the degree of the extension you get by joining the roots, I get an extension degree 1, 1, 2, 2. Let's see if I can persevere. Four, I'll do one more. And x cubed plus 1. By the way, you would join the 6th root of the unity. What do you suppose the degree of extension is there? This one's also. It looks like it might be 4 because you actually have to pick up both roots of these polynomials. However, something interesting happens if you have the roots of this. Notice this is a primitive 6 root unity. This is a primitive cube root unity. So a root of this is actually square of one of these roots, right? So you kind of get some stuff for free. And also, even if you just join this, you also get this by mucking around with the sound. Anybody see a pattern of numbers we're getting on the degree? The degree of figure. Right. So here we go from degree 1 to 1, degree 2, 1, degree 3, 2, 4, 2, 5, 4, 6, 2. Anybody want to consult the online integer sequences? Want to guess that one? What's that? It's the online encyclopedia of integer sequences, something like that. If you oil it up the brain, you might. Pattern seems to fall so far as going through function. Right? How many units are there in mod 2? It's 1. Units mod 3, units mod 4, there's 2 of them, units mod 5, 4, units mod 6. So, theorem. Okay, so let's let n be a positive integer and f a cyclotomic extension. So in other words, where this is the primitive integer of 1. Oh, there we go. 1. So I guess we decided that should become the first thing. F is an abelian extension. Okay, so it's a Galois extension. It's got an abelian Galois group. And what's the order of Galois group? D, where he is a divisor of your function then. Additionally, if n F number 3, ought KF, or ought F K, that way. Is isomorphic. This
you or did it just happen to occur for this first 6? Divide it.
This one, let's see. Well, let's look at an example. I think this is, I'll do this example anyway, and if it doesn't do what I think it's going to do, we'll look at another. Let's just review. So the first thing I'm going to do is I'm going to look at this a couple of ways. Or the P function of this is 4, right? I think I can see the structure here. So this is going to be, I can factor this. Do anybody know how to factor the first one? X4. It's a little tricky, right? I mean, you need a little bit of number theory. I won't come to this another way. Mind tries to. What am I saying? Well, I mean, you are going to have to introduce some more stuff. I think that works. But yeah, I mean, obviously, I could go way down. It's X4, it's gone, it's gone. Plus. And this is where. So. And of course, you can extract the roots here. This, of course, is polynomials are over Q. Right? And this is x plus I minus I. Now, what is the degree of the extension here? Well, in this case, I think it is the order of the function, actually, right? Because the roots of this, so the roots you get are and I'm going to the roots in another way of moment. One minus one. Right, we get these silly, of course, they're eight roots. We get about that. We go I minus I. And notice we're not primitive yet, right? All of these are eighth roots of one, but it doesn't require it, right? I mean, even I minus I only requires 4 pounds, right? These are the ones that take us all the way up there. And I get 4 other ones. I get minus radical 2. And actually, when we're dealing with discriminant, both these polynomials the same thing. It's going to be 2 minus 4, so it's going to be negative 2. And then radical 2. Now, I've got 8 roots of this, and here's kind of an important point. The polynomials, obviously would cycle always 8 roots, right? Because 1 and minus 1 are in the base field, and actually this is in extension 2. But let's take another look at that. Here's another way to write the roots, rather than doing the polynomials. Notice the roots we have x to 8. And so really, my roots look like this. So I should get 8 of these things before it cycles back, right? 0. Four power 4. Of course, the next power of 4 just loops back. Right? Notice this one is I, and this one is negative I, and this one is negative 1. Right? Keep it when you look down one. Isn't it? Okay. The roots, where the, if I'm gonna be able to Galois root this. What should I be looking at? If I want to look at the action on the roots. Yeah, I wish it was. These are the roots. Right. These are the roots of the x to the 4 plus 1 that we had over here that I split out here. But this is the biggest here, this chunk of this. All the other roots are powers of this. And some of the powers, particularly the even powers, all conform to lower ones, right? The 2 i's and 2 1's come out of this one. Let's see what happens, right? So it should be some action on these 4 roots, right? Let's do a little experiment. Notice that all these roots are powers of e to the I power 4. So in fact, maybe for convenience, maybe I'll call this Z cubed, Z5, Z7, because that's really what they are. And these are the 4 roots of x to the 4 plus 1, right? So let's induce this. Where does Z3 go? If Z goes to Z cubed, where does Z3 go? Was it? Well, if Z goes to Z3 or Z cubed, Z cubed needs to go to Z9, which is Z. That is correct. Agree. What about Z5? You know what happens to it. Z57, I agree. How about Z7? Where does it go? Well, given where the other ones go, this better work out. It does. What's the order of these isomorphisms? At 2, right? Everybody agree with that? If I compose this twice, I think. Okay, well, maybe I found the even. Let's try this one. Almost pitchfork. Let's try this one. Right, because remember, I mean, for every pair of roots, it has to be a transitive action. So there has to be something that fits. So there's something that fits in Z5. If Z goes to Z5, where does Z5 go? Z cubed goes to Z15, which is Z7. And Z7 goes to Z35, which is, what's the order of this object? This is also order 2. Now, let me point out that there can only be 4 automorphisms. Can somebody tell me why there can only be 4 of them? That's right. In this case, it's because the roots are powers of each other, right? Because here's the deal. Once I tell Z, and Z, you're going here, that tells me everything I need to know. That determines the rest. So where can I send Z? Well, I can send Z to itself and get the identity. I can send Z to Z cubed and get this. I can send it to Z5 and get that. Or I can send it to Z7 and get one more. So there's 4 automorphisms. So the Galois group is order 4. It's got 2 elements of order 2, so Galois group some more. Some percentages. And this jives with what we were talking about. Um, uh, Remember that last statement? The units of Z8 in this case are 1, 3, 5, 7. Not a coincidence. All right. And in fact, it's the full deal. Let me make a couple of remarks here, and keep in mind the theorem that we had about the cyclic extensions. So I'm going to close this out with a couple of remarks. I can remember. It states every abelian extension of Q is contained in some is contained in the cyclotomic extension. I find this to be really interesting. So if you've got any extension that has Galois and doing Galois group, you can find that inside a large enough root of unity extension. This theorem is not true if the base field is not Q. Even for a finite extension of Q, it would not be true, which has a little weirdness to it in my the second remark concerns radical extensions. And, you know, I've been kind of teasing you with this a little bit throughout the course, maybe a little bit of last, but we say that F is a radical extension. Okay, so F is a field extension. Okay, we say it's radical if UN where U1 and A1 is in K. And greater than 2 in Portuguese, for all J greater than 2, U sub J, AJ is in A, U1, U2. Okay, so let me tell you why I would do this. What this means is the first step. The first step from K to K U1. and the power of U1 is in K. Right? So say U1, A1, K. So this is equal to K of the A1 root of K. Right? I mean, so U is there. And then we build into K U1, U2, where U2 to the A2 is in K U1. So U2, the A2 is equal to something in here. And so I can have a base. So it's equal to, let's say, K0 plus K1 plus K2, A1, A squared, A1 minus 1, A1 root of A1 minus 1. So this U2 is the A2 radical, or K0, K1. So notice everything in the first field K is a linear combination, elements of K and in A1 groups, right? Everything in the second extension can be written as a linear combination of stuff in K1, which are these kinds of roots, times powers of this, which are roots as well. So the reason it's called a radical extension is basically everything in F can be written as a linear combination of roots of elements in the original field, right? And you may have to compose, right? You might have to take a root of a root kind of thing. In a radical extension, polynomial f of x and kx all its roots in F, radical extension, then f of x can solve by just like we did here. Any element, any root of this polynomial is in F, and elements of F can be expressed as perhaps extremely complicated radicals from the field. So when you ask yourself this, when can my polynomial be solved by radicals? Well, this is the condition you need. You need it to be in a radical extension. You need to be able to do this. And what does it take to be a radical extension? Well, it means it's a chain like this. Notice that these extensions, because of this condition right here, are cyclic extensions, right? And so of solvability needs solvable. Now what? Remember what it means. There's a bunch of different ways that solvable that you need a change normal subgroup such that the quotients are separate. That's one of the ways to talk about solvability. This is exactly this condition that you need right here. So, for example, you cannot get the roots if your Galois group is S5, right? You can't get from the rational numbers up to S5 by doing this thing, by joining successive groups, things, because that would mean that S5 would have to be a solvable group, because what you would get in the corresponding sequence of groups is you extract the solvable series. Okay. Any questions? Okay. The next bit is the last chapter we talked about. I'm going to talk about something called arithmetic rings. When we get maybe into synthetic domains a little bit. This is sort of a prelude to community algebra. So hopefully you all can take this, and some you can, some you can't. Hopefully you can take a couple of years if you can now. But this is kind of a prelude. So these are brains. So what I'm going to talk about will have a bit of flavor from the part of brain theory I like. It's kind of snuggling up to number theory a little bit. I hope that I have impressed upon you that algebraic elements report, right? It also it is very natural to ask in any kind of mathematics. Okay, how do you generalize, right? Fields are great, but they're really kind of boring if you like ideals, right? Because fields only have two ideals, and one of them is proper, and so that's zero in it. How would you generalize the notion of algebraic, which seems to be kind of a big thing, to a general ring? Well, we'll say a community ring. Definition. I think it's interesting the adjustment that has to be made. I'm going to do this in domains. And let me point out that since this isn't a community value yet, I'm going to do this a little bit more specialized. You can generalize this to rooms that aren't domains. But we will assume that we've got community ring identity, no non-zero zero divisors. We say, and this is the analog of algebraic. Over R, where T is a mnemonic polynomial. Now, the mnemonic business when we were on the field was just window dressing, because who really cares that much? But the only thing I can ever really remember using mnemonic for is if I wanted to say that the polynomial is unique, right? So if I have the irreducible polynomial of some algebraic element alpha, then minimal polynomial, if I demand that the polynomial be mnemonic, it's unique. right? So that just gets the scaling. Scaling is more because it is not just convenience when you're talking about community brain, because if I have a polynomial that begins in a 2, if 2 is not a unit in that ring, what are you going to do, right? You're kind of stuck. And actually, the monoid is an important thing right here. Let me point out that if R is a field, then P is central overall. It's known that P is out. If it's integral, it's clearly algebraic. And if it's algebraic, then all you have to do is divide out by the leading coefficient to make it a monic polynomial. And if you're in the field, there's no harm done. Right? Let me give you an example. Every element of Z from square root -5 is integral over to everyone. And I'll if I look at x squared minus 2ax plus a squared b squared. Roots a plus or minus b. Right. So if I pick any integers a and b, then there's your minus polynomial. Notice conveniently it's always quadratic, right? Oh, and let me also point out that this polynomial is not necessarily reducible. In fact, it's going to be reducible if b is not 0, because b is 0, and that's going to be x minus a squared. And of course, any element of z itself satisfies the easier one on x minus a. Yes.
So if you're for integral, are we required to this polynomial? You just have to be some,
I'm sorry.
like the polynomial does not have to be reducible.
Correct. It could be anything, right?
As long as it's not.
That's right. And again, it's good you put your finger on that, because actually some weird things can happen in certain situations. Right? Let me give you another example. Chemical. Ooh, I know some. Anybody give me some elements that are integral over there? Good. Notice, of course, if R equals T, any element is integral over itself, because, x minus R, right? So notice that Z is contained in the set of integral elements. And in fact, that's it. There aren't any others. And I'm gonna prove that for you real quick. Let us suppose A over B with GCD would be equal to 1. So I'm going to reduce the fraction, right? So suppose GCD of AB is 1, and this is and well, this means that A over B n plus m sub n minus 1, A over B n minus 1, n sub 1, A over B plus n sub 0, 0, with all the mi's in there. I hate fractions, so let's prove the denominator. Well, good with that. Now, let P prime bigger than 0 such that P divides. If P divides B, it divides this incredibly long thing right here, and it divides 0, right? So P divides A n, which implies P divides A, because P is prime. Therefore, P divides GCD of AB, which is 1. So no prime divides B. Therefore, A over B. So that's it. I agree with that. So the elements of the rational numbers that are integral over Z are just the elements of Z themselves. By the way, anybody look at that proof and tell me there is an easy generalization of this? I can replace Z by what? Anybody see? The only thing I really needed was to be able to divide out GCDs. I needed there to be primes. You do better. Any unique factorization will have the same problem. The elements, you have unique factorization domain, the elements of the quotient field and are integral over it are just the elements itself. And I will point out one last thing here. Notice 1/2 is a rational number that's a root of this polynomial, but it's not monic. So the monic business is incredibly important. Okay, any questions? Okay, your homework is due today at noon, but if you're running behind on it, I'm okay with turning it in a little bit late. I've got a 4th exam to go to. Anybody have any questions or want to skip to something later? Well, just light me up if I can help you out. Other than that, hope to see you in the math club. Have a good weekend.